Okay, let's go ahead and get started.
It's like an equation. You just use
We have an exam that opens up tomorrow morning and will stay open through Monday. Please remember that on Mondays, the testing center closes early, so you don't want to get stuck halfway through the exam and have them taking it away from you. Some of us are feeling overwhelmed, so much material. My goal today is just to help us all put it together. We're not going to cover anything new. We've covered everything that you need in order to be successful on that exam. But we're just going to practice today. The solutions to 2 sample exams are at the mat side. If you haven't already, I would encourage you sometime before you go to take that test exam A to do at least one of those and then grade yourself. And that'll give you some idea of how you will score on the real test. Those questions are at the same level, the same types of questions. And so that'll give you a good idea. Let's start with a word of prayer. If you don't mind, I'll offer that. Our dear Heavenly Father, we are so grateful for the opportunity which we have to associate one with another, to be here on this campus, to learn, to grow, and to help one another. We are grateful, Father, for the opportunities that we have to make choices, to make important decisions, but we also feel the weight of those decisions. We ask, Father, that thy Spirit might be with these young people as they face so many crossroads, that they might be guided and directed and supported. Please bless those who work with them, their bishops, and those who are in leadership positions, that they might know how to strengthen and help and encourage these young people at this difficult time in their lives. We ask now, Father, for a blessing of understanding, that our minds might be open, that we might be able to see the connections that are to be made, that we'll be able to see how everything fits together. And this we pray in the name of Jesus Christ. Amen. Okay. Some have wondered, how do I deal with all the equations? And I just want you to see the big picture, not all of the trees, just the forest. And the big idea is you want to find an electric field. And there's 3 ways to find the electric field. If the Klingon is a point, you use Coulomb's law. If it's a sheet of charge, you use this equation. If it's 2 sheets equal and opposite, you use that equation, where sigma is defined by that. It doesn't matter how you find your electric field, which of those 3 equations you use, you can always find the thing that we really care about, the force, by this equation. This is the definition of the electric field. Now, we're going to be working a whole bunch of voltage problems today, but always the same voltage problem. There's only one in the universe. And voltage problems we solve with energy, where I've got a kinetic energy bucket, I've got a gravitational energy bucket that we usually ignore if we're dealing with a proton or electron, and we have an electric potential energy bucket. And if we have uniform electric field near 1 sheet or between 2 sheets, we have the ED equation. And most of our voltage problems happen there. Those are the easiest ones to deal with. And then Tuesday, we talked about capacitance, and you had a bunch of capacitance problems on this last homework assignment. And then you've got your constants that you might need during that exam. Now, I hope everyone's recognized that there are two very different sets of charged plates, and they act completely opposite of each other. And so when you're dealing with charged plates, you got to ask yourself, which flavor do I got? Okay. The first flavor we call the insulated plates or isolated plates. Sometimes we use insulated, sometimes we use isolated. What that means is we charged up the plate and then we took away the battery. Without the battery, that charge is stuck there. Okay. It can't go anywhere else. The thickness of the charge on the surface of that plate doesn't change. If I put those plates closer together, the sigma has to stay the same. Now, if we go back to these equations, it's the sigma that causes the electric field. Epsilon naught is just a constant. It's just 8.85 times 10 to the minus 12. It's the sigma that gives me the electric field. And so if the sigma stays the same, the electric field has to stay the same. And so the field lines are the same distance apart. If that's 3 newtons for each coulomb, that's 3 newtons for each coulomb. Now, what doesn't stay the same is the voltage between the plates, okay? The voltage has to get smaller. Well, one way to see that is just from the ED equation. If the electric field stays the same, but the distance between the plates gets smaller, then the voltage difference between the plates has to get smaller. But that's just math. What I hope you see instead is the definition of voltage difference. It's if I reach into my pocket and if I pull out 1 + 1 coulomb, how much Verk would I have to do to push that from the negative plate to the positive plate? Well, in both of these cases, I would be fighting the same electric field. I would be pushing just as hard. But here I have to push further, and here I don't push as far. So I have to do less Verk to get that 1 coulomb across. And that's what voltage difference is. That's how I figure out how much I'm filling up that electric potential energy bucket. I do Verk and let that Verk fill up the bucket. Okay? Now, the second flavor is I charge up those plates with a battery and I leave that battery hooked up. I keep it hooked up. Now, the job of that battery is to keep those plates, if it's a 6-volt battery, to keep those plates 6 volts apart so that the voltage difference from the negative plate to the positive plate is 6 volts. Well, let me show you that. Remember, voltage is how much Verk I have to do for 1 coulomb to move it from some point A to some point B. In this case, from the negative plate to the positive plate. Okay? But we found last day that that Verk, and hence the change in voltage, is path independent. It doesn't care which path you take. So I'm going to take this path. I'm going to go up through that metal plate and into the metal wire. And I know that inside a metal, the electric field is 0. That means I don't have to fight anything. There's nothing to fight. So I do absolutely no Verk bringing that 1 coulomb through that metal. But if I want to take that 1 coulomb from the negative terminal of the battery to the positive terminal of the battery, that costs me Verk, okay? And it comes in the form of chemical Verk that we can't possibly understand unless we're in the chemistry building, okay? But that's what the battery does. And so as it goes through that battery, it takes 6 joules for each 1 coulomb to get it across. Now, then I'm back in the metal wire and in the metal plate, and that costs me nothing. And so the total path cost me 6 joules of Verk for each 1 coulomb. And a joule for each coulomb is a volt. And so that tells me that the voltage difference from the negative plate to the positive plate has to be the same as the battery. See if your neighbor is on the bus with that. See if your neighbor is okay.
It's like somebody think about like.
Okay,
They're very similar.
well, what if we move those plates closer together while they're still connected to the battery? Well, again, the battery's job, come heck or high water, is to keep the voltage difference from the negative plate to the positive plate at 6 volts. So the voltage difference stays the same, Now, what does have to change? Well, if I look at the ED equation, if the voltage difference from the negative plate to the positive plate stays 6 volts, but the distance between the plates gets smaller, the electric field has to get bigger to compensate. Saying this stays at 6 volts means I got to keep doing 6 joules of Verk to get 1 coulomb across, whether I'm going across here or whether I'm going across there. Well, I don't have to push as far here. If I got to do the same amount of Verk, I must be fighting a bigger headwind, a bigger electric field. Okay? Now, remember, electric field doesn't just exist by itself. It's caused by charge, by sigma, by the charge density on the plates. And so that means that the sigma must increase as I move those plates closer together. Well, how does that happen, Greg? Well, the battery makes it happen. Okay, the battery makes it happen. As I'm moving those plates closer together, what the battery does is it steals more electrons from this plate, making it more positive, and dumps those electrons on this plate, making it more negative. If I were to put a little flashlight bulb right there next to the battery, as I'm pushing those plates closer together, that bulb would light up because there would be a bunch of electrons rushing through it to get over to the other plate to create the larger electric field. When I got those plates together and stopped, the light would go out. And then when I moved the plates further apart, it would light up again because now the electrons are rushing back to where they started. And I could make a little light accordion with this. I could da 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 da. You wouldn't hear it, but then that's every day for me. Okay? Questions on this? Yes.
Can you just explain, so that equation at the bottom, E equals sigma over epsilon naught, like I am confused on how that correlates to pushing them together.
Oh, well, you see why the E has to get bigger. Okay. Well, epsilon naught is just a number. 8.85 times 10 to the minus 12. So if this gets bigger, that has to get bigger. And that is the charge, the thickness of the charge on the sheet. Okay? Okay. Other questions? Okay. So these two different flavors act almost opposite of each other. Almost opposite of each other. Now, the homework that's due tonight in tutorial 5, there's only 2 problems. And one of those problems is just like example 5 in your textbook. And the other one is just like example 4. We're going to start with example 5. And in example 5, we have 2 races going on. The first race is we let a proton go at A, and we see how fast it's going when it gets to B. We do it between these plates that are far apart, and let me remind you, the green plate is positive and the purple plate is negative. And the proton doesn't want to be next to the positive plate, so it's going to take off towards the negative plate. Now, if I move those plates closer together and let a proton go at this A, how fast will it be going when it gets to that B? Will it be going faster, the same, or slower? That's the first part of that example. Now, the second race is we take an electron and we let it go near the negative plate and we let it race over towards the positive plate. And right before it slams into that positive plate, how fast is it going? What's on its speedometer? Okay. And then we do the same thing over here. We let it go near the negative plate and see how fast it's going over there. Now, what you want to see whenever you close your eyes is that equation right there. That equation right there is the starting point for every single voltage problem dealing with an electron or a proton or something small. Okay, that's the two buckets. In order for one bucket to fill up, the other bucket has to drain. And winning the race means you got the biggest change in kinetic energy. And in order to have the biggest change in kinetic energy, you have to have the biggest drain of electric potential energy, and hence the biggest change in voltage. So if I can see which of those protons has the bigger change in voltage, I know which one's going to be going faster. Okay, does that make sense? Okay, well, let's look at our ED equation. Delta V from A to B is equal to the electric field times the distance from A to B. And those indices are everything. That keeps you out of trouble. That keeps you from getting 0 points on the problem. Okay? If I look at the electric field between these plates, and I remember, oh, that electric field's caused by the surface charge density, the sigma, and it's stuck on these plates. There's no battery. So the electric field stays the same. Well, guess what? The distance from A to B stays the same. If the electric field stays the same and the distance from A to B stays the same, the voltage difference from A to B stays the same, and it's a tie. Well, wait a minute, Greg. The distance between the plates got smaller. I don't care. The protons weren't going from plate to plate. They were going from A to B, and that distance did not change. On the other hand, the electron race was going from plate to plate, away from the negative plate and towards the positive plate, okay? And we know that the electric field stays the same, but the distance between the plates got smaller over here. And that means the voltage difference got smaller between these plates. And again, your gut should have told you that. Voltage difference is how much Varric I would do if I pulled 1 Coulomb out of my pocket and pushed it from the negative plate to the positive plate. Well, I don't have to push as far here. I got to push further here. So I get a bigger change in voltage over here. And so this electron's going to lose. This one's going to be going slower right before it hits the positive plate. Check on your neighbor. Do a buddy check.
Right now. Like, if you like,
Okay. But Greg, that doesn't look like our homework. Well, that's your homework right there. And I'm here to tell you that's no different than what we just did. Let me explain. I think of this in terms of your semester, okay? And suppose that the administration came and they said, we can't afford to keep the buildings open for 17 weeks during this semester. So we're going to lop off the last 3 weeks, send everyone home early. But here's the caveat. We're going to tell the professors that they can't cover any more material in a week than they normally do. We can't load these students down with extra work. Whatever you were going to assign in week 1, you got to keep assigning that in week 1. Well, during that new shorter semester, are you going to cover as many chapters in the book? No or heck no? Heck no. Okay. Now, this is not very different. Here, the administration comes and says, we can't afford 17 weeks. So we're going to send everyone home to spring break for 3 weeks. Go to a beach, do not study, just get a tan. Okay? And the professors can't assign any more work for each week. Again, because there's no electric field inside a metal, I don't have to fight anything. If I'm trying to take a 1 coulomb across here, I gotta fight, I gotta fight, I gotta fight. Wait, back up, back up. Okay, I want this one. Right here, I've got to fight, I got to fight. But then I get to the metal and that costs me nothing. And then I get over here and I got to fight, I got to fight, I got to fight, I got to fight. So it's exactly the same as moving the plates closer together. See if your neighbor bought that. No, he's not buying it.
76% done, bro.
Okay.
In the fifth metal rod are doing anything different.
Well, now let's look at the other flavor. The plates that are connected to the battery and keep connected to the battery. And again, we have the same exact 2 races. We race a proton from A to B, and we race an electron from the negative plate to the positive plate. And we ask who's the winner. Well, again, winning means you have the biggest change in kinetic energy, which means you experience the biggest change in voltage. Okay, so let's see which one has the biggest change in voltage. And let's start with the electron race going from plate to plate. The voltage difference is just going to be the electric field times the distance between the plates. With the battery connected, this voltage between the plates has to stay the same. Okay, that's fixed. And that means that if the distance between the plates gets smaller, the electric field has to get stronger, so that I'm doing the same amount of work going from the negative plate to the positive plate, whether I'm using that picture or this picture. Does everyone see why the electric field has to get stronger when the battery's connected? Okay. Now, what that means is that the electron race, it's a tie. Okay. When that electron smashes into the positive plate, it's going to be going exactly the same speed as this electron smashing into the plate. Okay. This one gets pushed for a longer distance. This one gets pushed by a stronger electric field, but it's a wash. It's a tie. On the other hand, when I look at the proton race, that voltage difference depends on the electric field and the distance from A to B. Well, the distance from A to B doesn't change, but the electric field got stronger. And so the voltage difference between A and B got bigger. Okay, and so that means that in this case, the proton's going to be going faster than the proton here. Now, another way of looking at that is to say, let's say it's a 12-volt battery. I just pulled that out of my left ear. Okay, 12-volt battery. If I look at the voltage from A to B here, well, first of all, is the voltage from A to B 12 volts? No or heck no? Heck no. I'm not going all the way from the negative plate to the positive plate. Okay. First of all, the voltage difference from A to B is going to be a negative number. And second of all, I'm only going a little less than halfway. So that's going to be about -5 volts from A to B. Okay. You know, if we use the analogy with gravitation, if it's a 1,200-foot mountain and you only go up halfway, you don't tell your friends I climbed a 1,200-foot mountain. No, that'd be a lie. You only went halfway. You went up 600 feet. Don't try to exaggerate. Okay. So in this case, if we're only going across less than half of the distance, it'd be less than half of the 12 volts. On the other hand, here, that's about 2/3 of the distance across. And so that's going to be like -8 volts. And so it's going to be a much bigger voltage and hence a bigger change in kinetic energy. Do another buddy check. Do another buddy check.
Figure out what you're even looking at. Okay.
Okay,
Going the same.
again, what does that have to do with your homework? Well, there's your homework right there. And again, I'm going to argue that that's no different than putting the plates closer together. My analogy is, again, the administration comes and says, we can't afford all 17 weeks. But instead of lopping off the last 3 weeks, we're gonna, well, let's back up. In this case, we lop off the last 3 weeks, but we tell the professors, you got to cover the same number of chapters in the semester as you did before. Well, what does that mean about your work in each given week? Well, it's all going to be crammed into 14 weeks. You're going to have to be working like crazy to get it all done. Okay. So the work during the semester, in this case, we call that the voltage difference, stays the same from negative plate to positive plate. In this case, your homework case, instead of lopping off the last 3 weeks, they give you a 3-week vacation in the middle. But again, they say to the professors, you got to cover as many chapters in the semester as you did before. That means you really have to work hard in the 14 weeks that are left. Does that make sense? Does that speak to your soul? Okay, good, good, good. That's your homework. I have an old exam question, and we're going to work through it really quick. I need helpers on this side. Thank you. And I need helpers over here.
Because we were.
Thank you. Whoop. Dude, falling down.
Oh my goodness. All right. Mademoiselle. I like preparing. Is the election? Your car. Yeah, that's the price. Last year, like 6, I don't know. He's like, yeah, but I got class.
Can I have some of yours?
Like, actually.
Okay, who needs some? Raise your hand.
That's true too. Like identify.
Some of yours.
Sauce. That's really voluntary to drop.
You got them? Okay.
What?
Was there a question over here? Nope.
We need.
Okay, raise your hand if you don't have one now.
Oh, where did you go?
I have it.
Okay,
It's under good.
thank you. Thank you so much. Okay, on the back of this, I've got an exam preparation sheet that's been posted at Max, just so that you'd have a hard copy of it. Let's work this problem together. What I've got. Oh. That looks upside down. Wow. Voila. Okay. We've got these parallel plates, and I kid you not, when this was on an exam years and years ago, the biggest problem people had was not knowing which side of that battery was positive. Okay. And it's a shame to be kept out of medical school because you don't know which side of the battery is positive. It's the long side, the long line. Why? There's no reason. It's just convention. People years ago decided that, and we just have to live with it. Okay. But that's going to be the positive terminal of the battery. And that means that this plate up here is going to get charged up positively. The battery is going to steal electrons from that plate and dump them on the bottom plate down here. Now, what that means is that the electric field between the plates is going to go from the positive to the negative, or down. Now, the first question we're asked, we're told that if we fire a particle, and this particle is not an electron, it's not a proton, it's not something small, it's big enough that we have to worry about its mass and its weight. But if we fire that right in the middle of those plates, we're told that it goes in a straight line at constant velocity, constant speed. Well, I hope from 105 that just triggers something in your brain. Ding, 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 ding. Constant velocity, zero acceleration. And that means that the force diagram for that has to be balanced, So if I draw a free body diagram for that, and that's actually part B, I would have a weight force down on the particle, and that's just the mass of the particle times g. And if I want a zero acceleration, the only other force on that particle is the electric force. And that has to be up. Okay, and that's by the plates on the particle. Now, I know that the electric force is just equal to the electric field times the test charge, the charge that's actually being pushed. Well, if the electric field is down and the electric force is up, well, that tells me my test charge had better be a negative particle. Got to be a negative particle. The questions on that? That's critical, okay? Whenever you have a positive particle that's being pushed, the electric field and the force are in the same direction. When it's a negative particle or charge that's being pushed, they're in opposite directions. Okay? That's not a question, that's just pointing towards the sky. Okay. In part C, we say, well, what if we took that negative particle and we fired it in between the plates, but closer to the negative plate on the bottom? Is that particle still going to go straight, or is it going to veer up, or is it going to veer down? Tell your neighbor what you think is going to happen. Is it going to veer up, away from the negative plate, down to the negative plate, or go straight?
Right. It's,
Okay. I hope what you said was that it's just going to go straight across, because the weight of that particle doesn't change. That only changes through diet or exercise. Believe me, okay? And the electric force doesn't change. Why? Because the electric field between two charged plates stays the same everywhere. It doesn't matter whether I'm looking close to the negative plate or close to the positive plate or right in the middle. I get exactly the same electric field, and hence I get exactly the same electric force. So it goes straight. until I pull those plates further apart. And because those plates are connected to a battery such that delta V stays the same, when the distance between them gets bigger, the electric field gets smaller. Okay, again, that's just from the ed equation. Okay, if I write down the ed equation, from the negative plate to the positive plate, it's the electric field times the distance from the negative plate to the positive plate. Well, if it's connected to a battery, the delta V between the negative plate and the positive plate stays the same. If this is a 12-volt battery, this is going to stay 12 volts. But if the distance between the negative and the positive plate gets bigger, the electric field gets smaller. And if the electric field gets smaller, then the electric force gets smaller. And if the electric force gets smaller, my free body diagram is no longer balanced. Now I have a net force down. Okay? And that means that that particle is going to do a trajectory that we've seen in physics 105 when we have a net force down. It's going to make an arc, a parabola actually, like we saw with projectile motion. Check on your neighbor. See if your neighbor could have gotten this problem completely right. Full points, full points.
But now that I'm
The word up there is they're large plates. And so if they're large plates, it's always going to be the same. Yeah, you're not moving them far apart compared to the size of the plate. When we say large plates, we mean way large.
not ready for the first one.
Okay. So really quick, is that pith ball positive or negative? Shout it out. It's negative. Yeah, sure it is. Okay. But what's going to happen if I bring that negative plate, again, this is the negative plate. If I bring it a little bit to the right, what's going to happen to that angle? Is the angle going to decrease, increase, or stay the same? With your clicker, okay, now you can click.
Negative ball. You bring the negative. It doesn't make sense to me. Just kind of like I suck at beat.
Okay. This is not rocket science. We did that last semester. Okay, last call. Get it done. Get your points. Is that all of us? Good, it stays the same. Well done. Well done. Okay. And again, the reason is because that's an insulated or isolated set of plates. There's no battery connected. So that means the charge density on the plate stays the same. And that's what causes the electric field. If the electric field stays the same when I move them closer together, the electric force stays the same. And so the angle stays the same. Now, what if these plates were connected to a battery? Well, then pushing them closer would increase the strength of the electric field. That would increase the electric force and the angle would increase. Question back here. I am changing the voltage between the plates, yes. But here we're looking for the force, not the voltage. When you're speeding something up and you want to know how fast it's going, that's a voltage problem. This is an F equals QE problem. Okay. Now, in your homework, the first problem in the homework that was due last night involved these two plates where you were told that there was an electric field in between the plates. Everyone got a different number. I'm going to use 7,500 newtons for each coulomb. And that's going to be the same no matter where I look between the plates. That's just, for large plates, that's just the way it is. Now, I'm going to give myself some writing space here. Okay, the first thing we're asked for is the voltage difference between the plates. And that's just really easy. Everyone had a different distance between the plates. I'm going to use 5 centimeters. But if I use the ED equation, the voltage difference from the negative plate to the positive plate is going to be the electric field strength times the distance between the negative plate and the positive plate. That's going to be 7,500. Instead of putting newtons for each coulomb, I'm going to put volts per meter. And then I'm going to multiply that by the 5 centimeters, but I got to do that in meters, 0.05 meters. And that gives me 375. The meters cancel and I get volts. Okay. Now, the next question, and this is an old exam question, that was only worth 2 points. Which plate, the positive one or the negative one, is at the higher voltage? Is that boring yet? Yeah, it's higher near the positive plate, always. Okay. But the next question says, if a proton is fired through a small hole in the negative plate straight towards the positive plate, how much would the electric potential energy of the proton increase as it travels across? Well, again, we have this equation where when we fill up the electric potential energy bucket from the negative to the positive plate, that's just going to be the change in voltage from the negative to the positive plate. That's how much I would fill up the bucket if I were taking 1 coulomb across. And then I multiply that by my test charge. Okay. And so in this case, the test charge of proton, 1.6 times 10 to the minus 19 coulombs. We found the change in voltage to be 375, volts. But a volt is just a fancy way of saying joules for each coulomb. And the coulombs cancel. And I get 6 times 10 to the minus 17 joules. Okay? Yes?
Is the equation for the change in electric potential energy really the same equation as the energy?
That's a what?
Is the equation for the change in kinetic energy really the same equation as the energy?
Oh, no. This is where it comes from. Varic external is equal to the change in kinetic energy plus the change in electric potential energy. And when we're dealing with a proton or an electron that we can't grab with our hand, this is the Varic done by your hand. If you can't grab it, this Varic is equal to 0. And if this is 0, these have to be the same size, but one's positive and one's negative. And so this is where you start all voltage problems. The change in kinetic energy from initial to final is exactly the same as the change in electric potential energy, initial to final, with a minus sign. If this is a +6, delta EPE has to be a -6, so that when I multiply it by a -1, I get +6. Okay? Now, the last question says, well, what if I fire a proton through a hole going 2 × 10⁵ meters per second? Will it be able to reach the positive plate? Well, how do I tell? Well, you remember this equation here is the buckets, where one is draining, the other one is filling. Now, typically in the past, we've been releasing particles from rest and letting them speed up because of the voltage difference. And that means that the kinetic energy bucket was filling while the potential energy bucket was draining. Well, this is the opposite. We're starting with a full kinetic energy bucket, and as that proton goes towards the positive plate, it slows down because we're filling up the electric potential energy bucket. Well, we know that if that proton had 6 × 10⁻17 joules of kinetic energy, it would make it all the way across, slowing down as it went, and it would just barely get to that positive plate, kiss it, and turn around and go the other way. Okay? If it had 6 × 10⁻17 joules. Well, let's see if it does. Let's see if it does. The kinetic energy initial is going to be 1/2 times the mass of the proton. I'm going to write that squirrely. And that's going to be 1/2. This number's on the front page of your exam. That's the mass of the proton. And we're told that the speed was 2 × 10⁵ meters per second. Remember to square that. More people lose points by not hitting the square button there. And this is going to give me 3.34 × 10⁻17 joules. Does it make it across? No or heck no. It makes it a little bit further than halfway across. And then it turns around and goes back. Oh, because the change in kinetic energy is the speeding up or slowing down. And so when the kinetic energy goes to 0, that means it's stopped. And we want to know, where does it stop? And I have a feeling, again, this is just a premonition, that you're going to need to do that on the exam A. Just a feeling.
What?
I'm rarely wrong. Okay. Okay, questions on this problem, this homework problem? Okay. What we're going to do now is I'm going to race through a bunch of problems that I think are useful getting ready for the exam. Now, whether we get through all of them or not is not important, because with each problem, I have put the answer in red on the slides that you have. Okay, so if we don't get through all of them, in the morning we almost got through, we didn't get through the last one. But if we don't get through all of them, you can go and work them and see if you get the right answer, because the right answer will be on the slide. So let's work through these. Through what voltage difference must a proton initially at rest be accelerated to reach a speed of 5 × 10⁶ meters per second? Tell your neighbor how you would start this problem.
Start it.
Good question.
Pretty soft.
Hi.
Any the different things on this one.
Well,
Not worth grabbing your feet. Oh, sorry. Here, it's a little bit of that. Calculate energy.
Yeah, that
Wait, are we actually?
Okay,
makes sense. Is negative.
voltage problems involving a proton or electron or other small particle always start the same place. The change in kinetic energy from initial to final is equal to the change in electric potential energy from initial to final with a minus sign. The minus sign is the one bucket filling while the other one drains. Zero sum game. This is going to be the kinetic energy final, 1/2 mv final squared, minus the kinetic energy initial. This is going, the minus sign comes down, and then this is going to be the test charge times the change in voltage from initial to final. And this is what we're looking for. That's where you get your points on this problem, finding that change in voltage. Now, we're told that it starts from rest, so that's zero. So really quick, let's turn on our crap detectors. Do we expect a positive or negative answer? Oh, Greg, you put the answer right up there. It's negative. Why would it be negative? Why would it be negative? Well, there's two ways to answer that. One is just a math way. This is positive. The right-hand side's got to be positive. It's a proton, so the test charge is positive, but I got this minus sign here from the zero-sum game. And that means if this is going to be positive, that change in voltage has to be negative. Now, the other way to see that is it's a proton speeding up. Protons speed up downhill as the voltage is getting smaller. When something's getting smaller, the change is negative. Think of your bank account. If your bank account's getting smaller, you're not happy, right? That's a negative change. Okay, so let's work this. It's a proton, so the mass is 1.67 times 10 to the minus 27 kilograms. We're told that we want it to get going at 5 times 10 to the 6 meters per second. Remember to square that. That's equal to negative 1.6 times 10 to the minus 19 coulombs times the change in voltage from initial to final. That's not physics. That's just math. That's just algebra. And if you solve that for the delta V, you get negative 130,000 volts. Okay. Now, folks, if you don't see how to get from there to there, it's going to be bad. Okay. It's going to be bad. Questions on that problem?
Like a history.
Okay, well, the next problem is very much the same. You have a pair of parallel conducting plates. They each have an area of 0.09 meters squared. We charge them up, positive and negative, to 5 times 10 to the minus 8 coulombs on each plate. And then we put them 1 centimeter apart. If an electron is released from the negative plate, at what speed will it strike the positive plate? Okay, well, let's go back and ask ourselves, how should we start this problem? Okay. Well, the answer is exactly the same as the last problem. That's the beginning place for all voltage problems because they're all the same. They're all the same. Okay. Only this time we're still starting it from rest, so this is still zero, but now it's the final velocity that we care about. Okay. If we know the voltage difference, we know everything else, we can find that speed. Well, how do we find the voltage difference? Well, it's between plates. And the voltage difference from the negative plate to the positive plate is just the electric field times the distance between the negative plate and the positive plate. Well, I know the distance is 0.01 meters, but I need the electric field. Well, between plates, I know that the electric field is equal to sigma over epsilon naught. And I know that epsilon naught is just 8.85 times 10 to the minus 12 Coulomb squared Newton meter squared. That's on the front page of the exam. But I need sigma. Well, sigma is just the total charge over the area. And I'm told the charge is 5 times 10 to the minus 8 coulombs, and the area is 0.09 meters squared. And that's going to give me a sigma of 5.56 times 10 to the minus 7 coulombs per meter squared. So I come back and I put that back in here, 5.56 times 10 to the minus 7 coulombs per meter squared. And when I divide by epsilon naught, I get an E field of 6.3 times 10 to the fourth. I'm going to write that as volts per meter. And then when I plug that in here, 6.3 times 10 to the 4 volts per meter. The meters cancel out and I get 630 volts. Well, now I come back here and I say 1/2 times, in this case, it's an electron. So that's going to be 9.11 times 10 to the minus 31 kilogram. That's on the front page of your exam. We're looking for this final velocity, and that's going to equal minus the test charge is a negative electron, and the voltage difference, it's going from the negative plate to the positive plate, so that's a positive 630 volts. And I'm going to write volts as joules for each coulomb so that the coulombs cancel. And now that's just algebra again. And if you solve that for the velocity, you get 1.5 times 10 to the 7 meters per second. And again, if you can't get from that messy equation to that final answer, it's going to be bad. Check on your neighbors. See if your neighbor's starting to worry about the test.
I know. It's super all about tedious process. For me, it's like using your it's tough to like process all of that and then turn it into I'm chilling with the energy.
Are there questions on this problem? Yes. Yeah, if this were a proton,
Last Monday,
first of all, a proton wouldn't race and speed up from the negative plate to the positive plate. It'd go the other way. And so this would be the 1.67 times 10 to the minus 27. This would be a positive number, and this would be a negative 630 because it's going the other way. Okay. Okay. We're going to change directions a little bit away from the voltage problem. In this problem, we have two small identical conducting spheres, and all three of those descriptors are important. It's small, meaning we can use Coulomb's law. It's identical, they're identical, and they're conducting, meaning the charge is free to move where it's happy. We start with those spheres carrying charges of plus 5 Q naught and minus 1 Q naught, where Q naught is just some amount. It might be a coulomb, might be a nanocoulomb, some fixed amount. Okay? These metal spheres are touched together. They were separated by a distance L. We bring them together and touch them, and then we return them to their original separation of L. What's the ratio of the strength of the force on either charge after they were touched to each other? compared to what they were before they were touched. And so with your clicker, there's a clicker question. You can click. And I'll give you a hint. E is not the right answer. Okay? E is not the right answer.
They like balance the charge. After they were, that makes sense. So then. They're gonna make. That's before they were touched.
Share chart, right?
They'd be like -1.
Yeah.
It's well, that's so. It's like so what it was before to what it was now. You know, like it's really good. Don't forget your level. They have a finger jar. I guess. Ask me one of one. I'm also thinking like, but Newton's third law, like. It should be 5 minutes. So well, I guess it is the.
I have no idea.
Total same.
Struggling.
Okay. Get your vote in.
Oh, it's like, yes.
Last call. Okay, we're all over the map. A is not the right answer. Okay, let's look at this. Because these are small, we can treat them as point sources. And that means we can use Coulomb's law, which you remember looks a whole lot like the gravitational force law, where it's the product of the charges instead of the product of the masses, but it's still a 1 over r squared force. Now, when we start out, we're multiplying 1 unit of charge with 5 units of charge. And the 1 is negative, but here that's not important. We're just looking at the magnitude of the force. But then we touch them together and the minus sign becomes critical. Because when we touch them together, they're metal balls. And that means the charge is free to commingle. The total charge is a plus 5 units and a minus 1 unit. When I add that together, I get a plus 4 units of charge. Now, the fact that these metal balls are identical means that when I pull them apart, there's no reason for one of the balls to get more charge than the other. So they're going to leave with 2 units on this one and 2 units on that one. And so now I'm going to be multiplying 2 units by 2 units. I think you can see that I started with 5 times a bunch of constants, and I ended up with 4 times the same constants. When I divide my final by my initial, I get 4/5. The final is 4 times the constant. The initial was 5 times the constant.
That's what.
That's right. Brindley brings up an important point. Protons aren't going anywhere, Greg. You know,
Yeah.
but a positive charge on a metal ball just means it's missing a bunch of electrons. Okay. And the other one has extra electrons. And so when you touch them together, the one ball was missing 5 units of electrons, and the other one had an extra 1 unit of electrons. So when you touch them together, the electrons move such that I'm only missing 2 units on this one, and I'm missing 2 units on the other one. But you can think of positive charges as moving. You get the same answer either way. Okay. It's sometimes helpful to do that that make-believe. Okay, let's look at this one. We have three equal positive charges that are at the corners of an equilateral triangle. Point P is at the midpoint between two of the charges. Let's call them Q1 and Q2. So it looks like this. That's Q1, that's Q2, that's Q3, and P is right between Q1 and Q2. Okay? We want to know the direction of the electric field at point P. And the choices we've been given are, it doesn't have a direction because it's zero. It's not zero and it's directed from P to Q3, so it'd be up. It's not zero and it's directed from Q2 to P, so it'd be left. It's not zero and it's directed from Q1 to Q2, which would mean right, or none of these is correct. So again, with your clicker, go ahead, you can vote now.
One of the sides bounce each other out.
Positives would be.
Point P would be positive, so that's how it is. Positive. Chicken bread. Talk about it. It's just always the same. So then positive is telling the positive.
Just the electric field, doesn't really matter.
Wait.
I think those two cancel negative.
Okay, get your vote in.
Yeah.
Last call. Okay, the correct answer is E. Good job, good job. Okay, now, folks, what is at point P? What is at point P? Nothing. Garnets. Absolutely nothing. Empty space. P is just an address, okay? But we're looking for the electric field, and the electric field has the waffle words. If I reached into my pocket and if I pulled out 1 coulomb and if I put it at P, how would it be pushed? Well, I think you could see that the positive charges Q1 and Q2, Q1's trying to push this 1 coulomb to the right, Q2's trying to push a 1 coulomb to the left. That's going to cancel out. And so the only push is going to be due to that positive source up there, and that's going to give me an electric field down. So the answer would be none of these options is correct. Okay? Check on your neighbor, see if your neighbor got that right.
I think that, oh, I didn't even see you. All these little red.
Not zero directed from P to what? Yeah.
Oh.
Okay.
I think it's just away from.
Let's look at another voltage problem. A proton is released from rest near a large single sheet of charge with sigma of 5 times 10 to the minus 5 coulombs per meter squared. What is its speed after it's traveled 3 centimeters? This is very much the same as the earlier problems, except that now instead of 2 plates, we only have 1 plate, but that's really the only difference. And so we're going to get some board space here. And again, I want to make this point over and over again. I don't have to erase the whole board. Okay? I still start with the same equation. the change in kinetic energy is the same as the change in electric potential energy, but with a minus sign. That's a zero-sum game. That's a one bucket filling while the other one ends. Now, we're still going to use this equation here, but now the electric field we'll need to find, and the distance it travels is 0.03 meters. And now the difference over here is that the electric field is due to a single plate. And for a single plate, I have a 2 there. And so that means I've got a 2 there. And we're told that we don't have to calculate the sigma in this problem. We're given the sigma as part of the problem. The sigma is 5 times 10 to the minus 5 coulombs per meter squared. And when I plug that in, what I get there is something that I can't do in my head. Surprise, surprise. That E field is going to be 2.82 times 10 to the 6 volts per meter. And when I plug that in here, 2.82 times 10 to the 6 volts per meter, I get a total here of 8.47 times 10 to the 4 volts. Now I go back here and I use the fact that it's a proton. So I use the proton mass. I'm looking for its speed. And it's a proton, so it's a positive 1.6 times 10 to the minus 19 coulombs. And it's speeding up. Well, what would the voltage be if this is a proton speeding up? Well, that's got to be a negative 8.47 times 10 to the 4 volts. I can write as joules for each coulomb. Now, when I did the ED equation, I just got a positive number because that was giving me the magnitude of the voltage difference. I got to use my gut to realize whether it's going into this formula as positive or negative. It's a proton speeding up, and they speed up downhill, or a negative change in voltage. And when I solve this for the speed, I get 4 times 10 to the 6 meters per second. That's all the time we have, folks. Let's stop here. There's one more problem. You've got 2 parts. You can work that, and the answers are at the backside. Remember that I love you.